All right, so welcome to today's physics video, more one-dimensional motion. Today we're going to be learning about acceleration. All right, so by the end of this video, you should understand what an object has to do in order to change its speed or its velocity. You should understand what an object's acceleration tells us about its velocity. You should be able to solve problems with these, four variables: acceleration, VF, VI, and T, which we'll talk about today. And then finally, you should understand what is meant when I say, and I will say this a lot this semester, or this year, make sure you think about your time interval, all right? That is going to be super, super, super important, all right? So we'll sort of start to crack that shell today. Is that a thing people say, crack that shell? I don't think it is. All right, anyway, moving on. Here we go, acceleration. So what is acceleration? All right. So far, in all the problems that we've done, our objects have been moving at a constant velocity, right? Like it'll say, whatever, Roy drives his car at 20 meters a second for 5 seconds, with the implication that he's always driving at 20 meters a second. And what that meant then was that the object's velocity, which, as I said, was constant, was the same as the average velocity. All right, but what happens if the object's velocity is not constant? Okay, what if the object is speeding up or slowing down or something? All right, well then what we have to do is we have to find what's called the acceleration. All right, so here's what acceleration is. Acceleration is the rate at which an object's velocity changes. All right, so to understand this definition, there are two important parts to it. It's the rate at which the object's velocity changes. All right, so the first part is this deal here, velocity changes. All right, so this is super important. Usually when you think of an object accelerating, you think about it speeding up, okay? If I say, hey, you need to accelerate, I'm just telling you to go faster, right? All right, in physics, that's not what it means, all right? In physics, the term accelerate is much more general. You can accelerate by changing your velocity in any way. So any change in velocity is going to be acceleration, okay? And so there are 3 different ways you can change your velocity, right? Because remember, velocity is speed and direction, all right? So what that means is in a car, or otherwise, I guess you don't have to be in a car for this to be true, but anytime you speed up, slow down, or turn, you are changing your velocity, right? And as a result, you're accelerating, okay? Now, this chapter, because we're dealing with one-dimensional motion, this turn option is really not going to be a possibility, right? Because if you're traveling along a straight line, I guess you could turn by, changing from going forwards and then change to going backwards. But realistically, an object can't go, 50 miles an hour this way and then turn around and suddenly start going 50 miles an hour the other way, right? Without slowing down, right? So anyway, I'm getting way ahead of myself. For us, at this point, largely we're going to be focusing on objects speeding up and slowing down. All right? We will not use the word decelerate for reasons that will become clear later today. All right? So try to take the word decelerate out of your vocabulary, at least for the purposes of this class. All right? So acceleration is the rate at which the object's velocity changes. All right? Now, the second part of this definition that was important is this word rate, all right? Remember, a rate measures how quickly something happens, okay? So acceleration here measures the rate at which this change, in other words, the change in velocity, occurs. It tells us how much the velocity increases or decreases per unit time, okay? So let's do a couple quick, just non-numeric conceptual examples, all right? So on this page of your notes here, I've got 3 different examples. So the first one deals with a Corvette and a school bus. All right, so if you have both a school bus and a Corvette sitting at a red light, and the light turns green, and both drivers floor it, they're both going to speed up, right? But clearly the Corvette's going to go zoom and shoot ahead of the school bus, right? That's because the Corvette is able to get from a speed of, in this example, 0 to 45 miles an hour very quickly. But the school bus, because it's so much bigger, it's harder to make it speed up, and so it's going to take more time to get to 45 miles an hour. All right? So notice, both vehicles eventually get to 45 miles an hour. They both achieve the same speed or the same velocity. The difference is how quickly they gain that velocity, right? Okay? So acceleration and speed are not the same thing, all right? It's funny because a lot of times you talk about sports cars and you go, whoa, that sports car is really fast. But in this example, the Corvette's not necessarily faster, it's kind of zippier. So, example number 2. All right, so now let's imagine two cars. Both of these cars are driving at 50 miles an hour, and both cars want to stop, all right? So, car A stops in the traditional fashion by slowly pressing the brake pedal, and, over, the course of a few seconds, the car slows down and eventually stops, all right? The driver of car B, instead, he stops his car by driving into a brick wall, all right? So, his car is going to stop very, very quickly, right? He's going to be going 50 miles an hour, and then bam, 0, right? In almost no time at all. All right, so again, both vehicles have a change in velocity. They're both going from 50 miles an hour down to 0. The only difference is car B changes its velocity much more quickly, and as a result, has a larger acceleration. All right, and finally, this third example really isn't relevant for this chapter, but I want to make sure that you understand you can change your velocity by turning, okay? So in this example, if you imagine two cars driving at 60 miles an hour, all right? Car A is on the freeway, okay, and it goes through a gradual curve at 60 miles an hour, no big deal. Whereas car B is driving down Jefferson at 60 miles an hour, and without slowing down, turns onto turns onto Fisher, all right? So that's going to be a really, really quick turn, right? Okay. So both cars are changing their velocity, right? They're going from, whatever, east to north or whatever, whatever it is. They're changing the direction by about 90 degrees, okay? But the difference is that car B is doing it very, very quickly. It's a quicker change in velocity, and as a result, a bigger acceleration, okay? So, example 3 can be a little bit confusing. We'll talk about that later on when we get to nonlinear motion, which is couple chapters off here. All right. Okay, so moving on. How do we calculate? Oh, sorry, I got ahead of myself. All right, so read these questions. Pause the video, read these questions, and answer them. All right, I'm going to assume you did that. All right, so question 1, can an object change its velocity without changing speed? The answer is yes. All it's got to do is turn. All right, in that last example, both of our cars were going 60 miles an hour, and they went from going east to going north. And since the direction is different, the velocity is different. All right. Number 2, can an object change its speed without changing its velocity? The answer is no, because as soon as you change your speed, you've changed how fast you're going, and thus you've changed your velocity. Okay? All right. So again, in a minute here, I'm going to pause it. So look at the situations below. If the object in the example is accelerating, write the word accelerating. If it is not accelerating, write constant velocity next to it. And I'm going to add on one other thing here. If it is accelerating, tell me why it's accelerating, like how it's accelerating. All right, so pause the video, go ahead and do that. All right, I'm going to assume you did that. So here, let's take a second run through the answers. Car speeds up from a stoplight is accelerating because it's speeding up, right? The velocity is changing. And this next one, the biker is accelerating because if he's hitting the brakes, that means that he is slowing down, right? A car drives straight north, so it's not turning, with the cruise control, so it's not speeding up or slowing down or anything. So that means that it is a constant velocity. All right, let's see, you're walking at 2 meters a second and you turn a corner without speeding up or slowing down. You are totally accelerating because you are changing direction, you're turning, right? All right, a flower pot falling off a windowsill is going to accelerate because as it falls, it will speed up. And similarly, a skateboarder rolling down a hill will be accelerating because they are speeding up. All right, so how do we calculate acceleration? All right, well, so to calculate acceleration, remember, it's the rate at which the velocity changes, okay? So the rate at which the velocity changes, that means how much does the velocity change per unit time. All right, so here's our equation for acceleration. This is the one that is on your little equation toolbox that I've hopefully passed out. If I've not yet passed it out, I will do that soon here. All right, and so what do the variables represent? Well, A obviously is acceleration. All right, VI and VF represent the initial and final velocities. Now here's where, well, and T is the time. All right, so that's what the variables stand for. here's where this idea of time intervals is going to become important. All right, the idea is it takes time for your object's velocity to change. Okay, so you know, in the example of the car driving into the brick wall, the VI would be 50 miles an hour, and the VF would be 0, and the T would be the amount of time that it takes from the instant that the car first makes contact with the brick wall going 50 miles an hour until the moment at which the velocity is exactly 0. Okay. So in these first examples, you know, the time interval is fairly straightforward. It's the time that it takes for the velocity to change. But sometimes it won't be quite so obvious. So you just need to make sure that you are visualizing the motion. And something I'll start encouraging once the problems get a little bit more elaborate is taking the time to make a drawing, particularly if you're struggling. All right, so let's do a quick example. For this first example, I'm going to use miles per hour again for the velocity. That will change by the end of this video here. All right. So here we go. A lot of car magazines are going to tell you the amount of time that it takes for a car to go from 0 to 60 miles. Well, 0 to 60 is the way they word it. This is just a measure of how long it takes the car to speed up from a dead stop to a speed of 60 miles an hour. All right, so suppose we've got a fancy sports car that can go from 0 to 60 miles an hour in 5 seconds. Let's find the acceleration. All right, so here's what's given. We know that it's going from rest, so our VI is 0. We know that our final velocity is going to be 60 miles per hour, right? Because that's what the car is speeding up to. And we know that this takes 5 seconds, right? Okay, so let's find the acceleration, all right? So acceleration is VF minus VI over T. So for us, our VF is 60 miles per hour. Our VI is 0 miles per hour. Divide this all by 5 seconds. On the top, you're going to get 60 miles an hour divided by 5 seconds, and you get 12 miles per hour per second. So there's our acceleration. Okay, so the acceleration is 12 miles per hour per second. What does that mean? All right. Well, remember, it's measuring the rate at which the velocity changes. So what it means is this. Every second, the velocity, you must, and this is going to be huge. I'm going to ask you to write this sentence out a gabillion times this chapter. So make sure you understand this. All right. And when you do it, you have to refer to the velocity. All right. So every second, what's the velocity doing? So in this case, the velocity increases. I know that because this acceleration is positive. In a minute, we'll do an example where the acceleration is negative. So every second, the velocity increases by how much? Oh, by 12 miles per hour. Okay? Every second, the velocity increases by 12 miles per hour. That's what this means. All right? I think with an honors class in particular, so many students are so reliant on the math that they neglect the concepts. That's not going to work for you here. All right? You really got to make sure you understand what this means. Every second, the velocity increases by 12 miles per hour. All right? So as a visual, let's think about it. Okay? Here's your speedometer, right? So at time 0, when the car is at the red light, the speedometer points to 0 miles an hour, right? And then what happens is every second, the speedometer goes up by 12, right? So it points to 12, 24, 36, 48, 60, right? So obviously drawing out these speedometers is not going to be the most practical way of doing it. So what we'll usually do is make a chart, all right? So here's the deal. 2 columns, time measured in seconds, velocity measured in miles per hour, right? So time 0 is when the problem begins, all right? Imagine standing there with a stopwatch and you're going to time how long it takes for the car to get to 60 miles an hour. You've got to start when the stopwatch says 0, right? All right, and then what's going to happen is we're going to take a look at what the velocity does each second. All right, and so the idea is the velocity began at 0, and then every second it goes up by 12. Okay, all right, so in this example, the car's acceleration is 12 miles per hour per second because, and I already wrote this on the previous slide, because every second the velocity increases by 12 miles per hour. Okay, so that is that. All right, so let's talk about the units. So the problem with that previous example is that we used miles per hour, right? The acceleration came out in miles per hour per second, all right? But the problem is miles per hour isn't metric. So from now on, we're going to measure the velocity in meters per second. So instead of getting miles per hour per second, we're going to get meters per second, all right? So here we go. We get a car driving at 23 meters a second, and the driver hits the brakes. After 4 seconds, the car is only going at 11 meters a second. Let's find the acceleration, okay? So, same exact process we just went through. Write out what you're given. Starting velocity of the car was 23 meters a second, because that's how fast it was moving when it began accelerating. The problem tells us that it's going to accelerate for 4 seconds until we get to a final velocity of 11 meters a second, and we want to know what the acceleration is. So, plug in your numbers, right? A equals Vf minus Vi over t. The final velocity we get to is 11. The starting velocity was 23. The time this took was 4 seconds. So 11 minus 23 is negative 12. So what this means is our velocity decreased by 12 in 4 seconds. So we get negative 3 meters per second. Okay? So, what does this mean? Well, it means every second the velocity decreases by 3 meters per second. All right. Now, we will usually do this. So a quick little bit of algebra. Meters per second is the same as meters per second divided by seconds, right? Meters per second, which is the same as meters per second times 1 over seconds, which is meters per second squared. So this answer up here, oh man, smartboard is not being smart. All right, so negative 3 meters per second, we will always write as negative 3 meters per second squared. And that is how we'll say that. Negative 3 meters per second squared. And just in your head, you should think, oh, that means the same as negative 3 meters per second. It's measuring the rate at which the velocity changes. Okay? So, all right, suppose we wanted to go the other way. Suppose I gave you the acceleration and we were trying to find something up. All right, so in this example, we've got a car that's driving at 27 meters a second. The driver hits the brakes, causing the car to accelerate at negative 4 meters per second squared. Find the velocity of the car after 6 seconds. So start by writing out what you know. Vi is 27 meters a second. This 4 meters per second squared is an acceleration, right, because of the units. And this is going to happen for 6 seconds. And the question wants to know what's the final velocity. All right, well, one way you could do this, and it's totally impractical, but I like this method because it shows me that you understand the concepts. One way that we could find the velocity is to make a little chart. Time, velocity. And the idea is at time 0, the car's velocity is 27 meters a second. Okay, so to find the velocity after 6 seconds, I can, well, let's see. The velocity is going to decrease by 4 every second, right? So just keep subtracting 4. You get 23, 19, 15, 11, 7, 3 meters per second for a final answer. Okay, so that's one way of doing it. And again, not practical, but I like it because in order to solve the problem this way, you have to understand what acceleration is. All right, now here's another way of solving the same thing. Let's go back and write down what we know. We know our VI is 27 meters a second. We know our acceleration is negative 4 meters a second squared. And we know the time is 6 seconds. And we're looking for our final velocity, right? So we have an equation that ties these variables together, right? The problem is we're not looking for acceleration. We're looking for VF. So let's do a little bit of algebra. I apologize for making that voice. All right, so we're going to multiply both sides by t. You get AT equals VF minus VI. So to get VF by itself, I got to add VI to both sides. So AT plus VI equals VF. I will usually rewrite that as this. I will even write it in green. VF equals VI plus AT. This is another one of the equations that is on your toolbox. Memorize it, or better yet, understand it. All right. What I want you to see here is that this equation does the exact same thing that we just did by using the chart. All right. So let's plug in the numbers so you can see what I'm talking about here. So check it out. Let's see. Our velocity VI is 27 meters a second. That means that we began at 27 meters a second. And then our acceleration is -4. That means we're going to decrease by 4 meters a second every second. Let's see, the time is 6 seconds for 6 seconds. So we're going to start at 27 and then subtract 4 6 times. Look what we did on this chart back here. We started at 27 and we subtracted 4 1, 2, 3, 4, 5, 6 times. Okay? So this equation it's literally the same thing. You get 27 plus -24 gives you 3 meters a second, right? Sorry, I'm sloppy about my units here. Okay? All right, so there we go. I think I'm going to stop here because I'm already over my 20-minute cap. Why don't you guys do this example on your own, and we'll start with it tomorrow. All right? Cool.